Hello everyone, this is the fifth lecture on the force measurement, and in this specific lecture we are going to learn about the measurement of the torque, which is the continuation of the previous lecture, and this is the part of the subject called mechanical measurement and the metrology. So the contents of these specific lectures are the eddy current dynamometer, the torsion dynamometer and the servo control dynamometer. Basically we are going to learn about the three dynamometers. Now let us start with the very first dynamometer, the eddy current dynamometer. Now what is the basic principle of this particular dynamometer? The principle says that the power loss produced on account of eddy currents, which is generated when the rotating conductor cuts across the magnetic flux. Okay, so let us understand each and every part one by one. Now what is the magnetic flux? Magnetic flux is basically generated whenever the permanent magnet or the temporary magnets are there. Okay, now conductor means any kind of conducting material. It can be in terms of the disc, it can be in terms of the plate. Okay, so any kind of conducting material, like let me say a copper, this is a copper disc. In that case, whenever this kind of copper plate or copper disc cuts across this kind of magnetic flux, in that case some eddy currents are generated. That means some reverse flow is generated which will be trying to resistance the existing current. Okay, and due to that some power loss will be generated. Okay, so if we can measure that particular power loss, we will be able to measure the torque across this particular shaft that is available here. Okay, so this is what the basic principle of the eddy current dynamometer is. Now remember that many times instead of eddy current there is one more word used, that is called Foucault's currents. Okay, so Foucault's currents and the eddy currents are both the same thing, and also remember that eddy currents basically works on the Faraday's laws of induction. Okay, so this is what we need to understand. And secondly, when we talk about the eddy currents, basically eddy currents actually gets dissipated in terms of the heat. Okay, so whatever the power that is absorbed from the shaft will be rejected in terms of the heat. So when we talk about the eddy current dynamometer, it is basically the absorption type dynamometer. It will be the absorption type dynamometer. Okay, so this is what we need to remember. Now let us understand construction and the working of the eddy current dynamometer. So basically an eddy current dynamometer consists of a toothed steel rotor which is fixed on the engine shaft. This is your engine shaft and this is the toothed rotor. Now rotor means what? It will going to get rotated. So whatever the rotation speed engine shaft is having, the same rotation speed will be there to this particular rotor. Now what do we understand from the toothed rotor? Toothed rotor means something like this. Okay, this is called the toothed rotor. It looks like a gear. Okay, so this is what we understand by the toothed rotor. Okay. Now, this particular toothed rotor basically available inside the stator, which is made of the cast iron. Okay, we can also say this as a casing because it acts like a enclosure for this rotor section. Okay, now the exciting coil is actually fixed with this particular stator, or we can say casing, with the help of one groove. Okay, now this is an exciting coil. When we see this particular word, remember this is the exciting coil, not the exiting coil. Okay, now this particular exciting coil is available with the external power supply. Okay, so there is some external power supply available with this particular exciting disc. Now this exciting coil will be energized whenever we want to use the dynamometer with the help of the external source. And also this stator that we are talking about is actually mounted on the shaft with the help of the anti-friction bearing. So this will not rotate with the shaft, as this is mounted on the shaft, but still it will not rotate with the shaft. Okay, so this particular thing is called the eddy current dynamometer. This is what the construction of the eddy current dynamometer is. and this is almost the same figure. You can see there is a rotor available, okay, there is a stator available. Over here there will be the energizing coil or say exciting coils, okay, and this is the supply for these exciting coils, okay. And over here you can observe that there is a lever available, extra length available, which will be something L, let me say, and there is a force measuring device available which will give us the value of the force or say value of the torque that is going to be generated with this one, okay. So this is the whole construction of the eddy current dynamometer. Now let us understand how this eddy current dynamometer will work. So basically when this particular dynamometer is operated, the rotor starts to rotate because it is fixed with this particular shaft. So whatever the speed that shaft is going to obtain, the same speed will obtain by this particular rotor. Now over here this is the exciting coil available, which is actually excited with the help of the external power source. Now due to that, what will happen? Some magnetic field will be generated across this particular exciting coil. Now this magnetic field will cut by this particular rotating rotor, okay, because it is the toothed rotor, it will cut the magnetic field. Due to that, now the flux at all the point of the stator will change and some voltage will introduce as a local current, okay. So over here this local currents will be generated, and these local currents are basically known as the eddy currents, which will flow in a short circular path around this particular stator. Now these particular currents, very small currents, actually tends to stop the rotation of the rotor, okay. So basically this rotor RPM are going to reduce, but as we know this rotor is connected with the shaft which is having a torque, okay. So due to that, what will happen? The reverse scenario will happen. Rotor will not reduce its RPM, but this stator will start to rotate in a reverse direction. So basically it is having the tendency, the stator is basically having the tendency to rotate in a reverse manner. So if I say the rotor is rotating in this particular direction, if I see this figure, if the rotor is rotating in this particular direction, what will happen? The stator will try to rotate in this direction due to the eddy current forces, okay. So this is what will happen. Or if we say the rotor is rotating in this direction, in that case the stator will try to rotate in the opposite direction, okay. Now this opposite direction torque, okay, will be measured by this particular force measuring device, because this also try to move this whole assembly, okay. So this is how the force and the torque will be measured with the eddy current dynamometer. Now the operating range of this specific dynamometer is up to 6000 RPM. So this is made for the higher RPMs, and it can measure up to 250 kilowatts of the power. So this is the range of this particular eddy current dynamometer. Now due to that, as it is the electrical eddy current dynamometer using the electrical components, it has some of the very basic advantages that are mostly available in the electronic components. Very first, it is having the smaller size for the same capacity. If you want to make a Pronin brake dynamometer for the same capacity and the eddy current dynamometer for the same capacity, in that particular case eddy current dynamometer will have a very small size. Secondly, as it is having a higher speed range, it is basically suitable for the large speed ranges, and it has a good control over the low rotating speeds also. Okay, so this is all about the eddy current dynamometer. Now let us understand the torsion bar dynamometer. Now the torsion bar dynamometer is basically uses the principle that whenever any kind of rotating element, like let me say the shaft is there, is trying to create a rotation, okay, this is the generator from where the source is available for the rotation, and this is the second free end, okay. So whenever it is trying to generate the rotation, in that particular case, the second end will try to resist that rotation due to some of the inertia phenomenon. Okay. So what will happen? It will try to resist this particular rotation. So what will happen in the intermediate part of the shaft, some twisting will be generated, or we can say that torsion will be generated. Okay. So if this particular part has rotated around 360 degree, there are chances that due to this particular resistance, what will happen? This particular section may have rotated only 359 degrees. Okay, so this particular 1 degree is basically the twisting of the whole shaft, and actually the twisting of this particular shaft is directly proportional to the torque that is being generated. Okay, so we can actually calibrate this twisting with the torque in this particular case, and the same principle is applied in the torsion bar dynamometer. Okay, so basically what is happening over here, the 2 points, let me say this is the first point and this is the second points, at the distance of the L are selected. Okay, and the twisting between these 2 points is measured, and this particular twisting is calibrated in terms of the torque. This is what basically happens. Okay, there are 2 dynamometers that are available for the torsion bar. The very first is the mechanical torsion meter and the second is the optical torsion meter. We are going to understand the mechanical torsion meter only in this particular case. So let us understand how the mechanical torsion meter works. So over here you can observe that this is a shaft available. Now on this shaft one disc is mounted. So one disc is fixed, which is actually rotating with this particular shaft. Now at the point number 1, this is the point number 1, one pointer has been kept and which is extended up to this particular disc. Okay, so this is the pointer which will show the readings on the calibrated disc. There are some readings available which are actually calibrated in terms of the torque. So this will show us actual the angle, but this particular angle is actually calibrated in terms of the torque, and the torque is written on this particular disc. Okay, so if you want to measure the torque will be calibrated, and if you want to measure the power will be calibrated over here. Now whenever the shaft will start to rotate, what will happen? This pointer will also rotate and this disc will also rotate. Now as you can observe that there is some distance between the pointer and the disc. So what will happen? Some angular torsion or say angular twist will be there between these 2 points, and due to that this pointer will show some value. Now as you can see or as you can observe that actually everything, the disc, the pointer and the shaft is rotating, so we can't directly see that particular value. So we are actually using the stroboscope, which is the RPM measuring device, to actually see the value that is available on this particular calibrated disc. And as the stroboscope will be used, what will happen? The image will be seen something like this. So basically stroboscope will show us the still image and we will be able to see the value that is available on the calibrated disc. This is how the torsion bar dynamometer will work. So basically when we talk about the torsion bar dynamometer, this kind of dynamometer are used whenever we want to measure the large power. Okay, large powers will be measured with this kind of dynamometers. So whenever we want to measure the power of the steam turbine or say propellers that are available in the naval ships, in that particular case we will be measuring those powers with the help of the torsion bar dynamometers. So this was all about the torsion bar dynamometer. Now let us talk about one more dynamometer which is known as the servo controlled dynamometer. So servo controlled dynamometer is not a special kind of dynamometer. This is the dynamometer which is actually available. Okay, now this can be any kind of dynamometer. Now this dynamometer is actually made such a way, or say with the extra attachments, it is made such a way that whatever the power we actually required will be automatically adjusted with the help of the arrangement that is available with this particular system. So this servo control mechanism will make the whole system automated. Okay, so this is what happens in the servo control dynamometer. Okay, so let us understand what is exactly a servo control dynamometer. So basically this kind of dynamometer are used to test the engine in the laboratories with the artificial creation of the actual torque and the speed variation of the actual automobile engines. Okay, so you can observe that this is the test rig where we are having the test engine which is available over here. Okay, now this test engine is connected with a dynamometer which will measure the power of this particular system, or we can say the torque of this specific system. Now this torque is sent to a control unit. Okay, and the control unit will actually observe the data, and by observing the data it will actually send that particular data to the controller. Then after this controller will send some information to the servo motor which actually changes the values in the test engine. Okay, so basically servo motors are working as an actuators over here. Okay, so this is what happens in the servo control dynamometer. Now in this particular line diagram you can observe that this is a dynamometer which is available over here. Now what will happen, the actual RPMs of the dynamometer, or we can say of this particular shaft which is running by one engine, is measured by the tachometer generator. Okay, now these are the actual speed which is recorded by the tachometer generator. Now this speed, let me say this particular speed is 1500 RPM and I want a speed of the 2000 RPM. Okay, so this speed is actual recorded speed. Now this is the speed that I want. Now I will put this speed in this specific tape recorder. Okay, so I have recorded this speed 2000 RPM in this particular tape recorder. Okay, so what will happen over here, the actual speed signal will be sent to the system, and over here the desired speed signal which is 2000 RPM will be sent by the tape recorder. Now what will happen, whatever the signal will be generated will be added or subtracted by over here. This particular point is known as the summing point. This is the whole control system which you will learn in the control engineering subject, which will come in the 3rd year. Okay, so this is the summing point which will actually generate the output signal by adding and subtracting the value. Now over here you can observe that the actual speed is 1500 RPM and the desired speed, the speed that I want, is basically 2000 RPM. So what will happen over here, the values will be ultimately 500 RPM less. Now this 500 RPM less value will be known as the error signal. Okay, and this particular error signal will be sent to the controller. Now this controller will check that this is the 500 RPM signal which is actually the less value. Okay, so I need to increase the 500 RPMs more. So this controller will send the information to the servo motor that increase this RPM by 500 RPMs. Okay, so try to increase the RPM or continuously increase the RPM. So this process will continue till the tachometer receives exactly 2000 RPMs. Okay, once it receives 2000 RPM, the whole system will stop its working, or say whole system will send the 0 RPM error message. Okay, so this is what will happen in the speed control. Now secondly, dynamometer is also measuring the torque. Okay, so what will happen, whatever the value of the torque that is generated over here will be sensed by the load cell, and the load cell will send the actual torque data to the system, and the desired torque data that is recorded by the tape recorder that we actually need will be sent from here. And the same thing will happen, whatever the error signal that will be generated will be sent to the system. Okay, if the error signal is negative, the controller will send the positive data to the system. Okay, so if the torque is less, then the controller will send the data to increase the torque to the engine. Okay, so as the engine receives the information, the servo motor available over here will increase the torque. So this is what will happen to the whole system. Now, as you can observe, the whole thing is happening automatically. Okay, so basically the whole mechanism, the servo control dynamometer is an automated dynamometer where the dynamometer is placed in this particular part, and with the dynamometer we are having the whole control system adjusted, and that particular control system will automate the whole dynamometer. So this is what happens with the servo control dynamometer. So we have completed all the dynamometers over here. This is the end of this session. We will meet in the next session. Till then, keep learning. Have a good day.